We saw Jacobson's rank, which lets us do rank queries in constant time with little o of n additional bits. Now we need to look at the select counterpart, which is called Clark's select. So let's just remember that unlike rank, with select, we're going to be dealing with offsets, right? So the input to the select query is a rank. The output is the offset of the one that has that rank, the set bit that has that rank. So when we go to divide, we're going to similarly, just like Jacobson's rank, we're going to divide the bit vector into chunks. But those chunks are going to be defined based on how many set bits they have, not how many bits they have, right? So we're going to divide our chunks according to how many set bits they have. Also, there's going to be sort of two layers. So with Jacobson's rank, we had a notion of a different thing that we were doing for the sparse chunks versus the dense chunks. Here we're going to have to do things in sort of like two layers, where the upper layer is going to distinguish sparse from dense, but then within dense, we're going to have to do another bifurcation of dense, sparse, and dense, dense. So you'll see that. And then the answer is going to be an offset. Right? So the input is a rank and the output is an offset. So when we go to build our lookup tables, you know, the kinds of tables that we were building for Jacobson's rank, we'll build similar tables here, but those will be tables of offsets and sometimes relative offsets. Quick reminder of what the select query looks like, right? We already showed these examples, but the select query, whereas the rank is taking a offset and returning a rank, which is the number of times that in this case is 0, appeared previously in the bit vector. The select queries are taking a rank and returning an offset. So for select sub 0 of 3, that's essentially saying, give me the fourth 0. What's the offset of the fourth 0? And that's this 0, so it's giving me offset 7. This is saying, give me the offset of the fifth 1. 1, 2, 3, 4, 5. So it should point us, no, sorry, the sixth 1. So it should point us there. So the select query takes a rank and gives a offset. Okay, don't be frightened, but this is what the this is what the outline of the method looks like. Except, let me just, before we go any further, I'm really just showing this because I want to argue that it has kind of this shape. And let me see if I can draw the shape. Here's like the root, and then the first thing we have to do is we have a bifurcation here, depending on whether what we have is a sparse chunk or a dense chunk. And if we have a sparse chunk, we can finish quickly, right? We actually only have one lookup table that we have to make. Over here, if it turns out we have a dense chunk, there's another layer where we have to distinguish between, we now have to take the chunks and divide them up into subchunks, and then we have one approach for the sparse subchunks, another approach for the dense subchunks. So this is chunks, and then this is subchunks. I'm going to use the same chunk, sub-chunk language as I used for Jacobson's rank. So I just want to show you it has this general shape. And we're going to start here with the simplest case. Okay, so the part that's highlighted here, that's where we're going to start. Okay, so let's talk about how to divide the bit vector up into chunks. So let's say, again, this is our bit vector of length n. We're going to take this and split it into chunks, each containing log squared of n 1 bits, set bits. Okay, so this is different from before. Before, with rank, we divided it into equal size chunks, equal size, equal number of bits. This time we're dividing it into like equal, what should we call it? Equal weight chunks or something like this, where the weight is how many set bits there are in the chunk. So of course those chunks are actually going to be different lengths, with speaking in terms of how many total bits they have. So it's going to look more like this. You know, it's going to divide it up into chunks, but those chunks are various lengths. So if it turned out, for example, that log squared of n was 3, not a very realistic scenario, but let's just say that the log squared of n was 3, that would mean each of these chunks had 3 set bits in it, you know. Right? Each of those has 3 set bits. Okay? The larger chunks, where the ones are more spread out, right, they all have the same number of ones. So if the chunk is larger, that means those ones are more spread out. They're a smaller fraction of the total number of bits in that chunk. Then they are sparse. Chunks that are shorter, that means they have the same number of ones but spread out less. Well, those are the denser ones. We haven't drawn a specific dividing line yet, but that's the idea. We have these chunks. Some of the chunks are sparse. Some of the chunks are dense. Okay? So the first thing we want to do, each of these chunks contains a predictable number of set bits. It has log squared of n set bits. And we know n, so we know log squared of n. So for each of these chunks, we can store an offset of the chunk's start, right? So up to here, and up to here, and up to here, right? So these offsets in this example might be, here's a longer chunk. Let's say this offset is like 80. Then here's a shorter chunk. Maybe this is like at 88. And then here's like a medium-sized chunk. Maybe this is like at 130, right? Just making up some numbers. But we're going to store for each chunk its offset with respect to the beginning of the bit vector. So let's say that that's what's inside these purple boxes that I've drawn here. Okay? And we take all these offsets and we store them in an array, right? And how are we going to use this array? Well, the very first thing we're going to do when we have a query, remember the input to a query is a rank. We're going to take that rank, divide it by the number of set bits per chunk, and that tells us which chunk we're in, quote unquote. So we'll do a division to figure out which chunk we're in. And then once we know that, we can simply look up what's the offset of that chunk. And we haven't solved the whole problem yet. We still have to deal with where we are within that chunk. But we've solved a piece of the problem. We now know that the offset up to a certain point. Okay, so let's think about how much space this takes in terms of big O. Okay, so we're going to store one of these things for each chunk. So how many chunks are there? Well, it depends, right? Because we have one chunk for every log squared of n set bits. I guess in the worst case, most of the bits are set. Maybe almost all of the bits in the entire bit vector are set, such that the number of set bits is actually approaching n. Okay, in that case, the number of chunks is approaching n over log squared of n, right? It's kind of like the worst case number of chunks that we have, total. And then for each chunk, we're storing an offset. And this is an offset with respect to the original string, so we need the full log n bits to store that offset. So we're going to multiply this by log n. Okay, so we have big O of, let's just cancel those two, n over log n, which is little o of n bits. Okay. All right, so we're not breaking the bank. We are not exceeding our target of little o of n bits of extra space by storing these offsets. We're good. Okay, so we can store these offsets, and so far so good. Okay, now we need to talk about these chunks and which of them are sparse and which of them are dense. And the dividing line we'll draw is that chunks that are longer than log to the fourth n bits are sparse, and chunks that are shorter than log to the fourth n bits are dense. So in this example, all right, I haven't showed you exactly how long these different chunks are, but let's just say the dividing line ends up being here, where that dividing line corresponds to everything that's shorter than log to the fourth of n is up there, everything that's longer than log to the fourth of n is down there, which means that these are the dense ones above the line, and these are the sparse ones below the line. Okay. Why this log to the fourth of n, right? We're starting to get exponents that look a little arbitrary here, but actually it's not arbitrary. Log to the fourth of n is the square of the number of set bits per chunk, log squared of n. So this should remind us of something we saw previously in the Jacobson's rank, which is that when we go to draw our sparse versus dense distinction, it's basically going to be driven by what proportion of the bits are set. So if more than square root of the total number of bits are set, that would be dense. If fewer than square root of the total number of bits are set, that would be sparse. All right, so defining the dividing line between dense and sparse by saying log to the fourth of n bits is another way of saying we're going to divide into dense and sparse according to whether the fraction of set bits is greater than or less than the square root of the total number of bits, given that the number of set bits is log squared of n. Okay, so what are we going to do? We said the easy case was the sparse case, right? These dense ones up here, we're going to have more to do, right? There's several slides about what we have to do with those dense chunks. The easy ones are the sparse chunks, the ones whose length is greater than log to the fourth of n bits. Those are the ones where it's okay for us to pre-calculate all of the offsets of all of the set bits, okay? So, all right, in order to show that that's, okay, we have to do the big O of how many bits we're actually storing in order to pre-calculate all those answers. And we have to argue that it's little o of n bits. So let's do that real quick. So let's say, first of all, how many of these chunks might there be? So we're asking specifically now about sparse chunks. Okay? But now we have a clear vision of how many there should be because each of them is at least log to the fourth of n bits long, right? So how many can there be? Well, at most, n over log fourth of n. That's how many of these sparse chunks there could possibly be. How many bits do we need to store an answer? Okay, it's log n. You might be thinking, though, since before we used this trick where we could sometimes store relative ranks for Jacobson's rank, you might think about whether this is one of those situations. Maybe within the sparse chunks we could store a relative offset, but actually it turns out no. And if you think through the worst case, right, the worst case for this term is if the all n bits of the bit vector was just one giant sparse chunk. Right? If that's the case, then obviously you can't get away with any better than log n bits in order to store an offset within that chunk, because the chunk is the whole bit vector. Right? So we actually, because we haven't upper bounded how many bits can be in a chunk, right? The chunks are at least log to the fourth of n, but there's no upper bound. We can't use that relative offset trick here. So we just have to live with saying that the number of bits to store an answer is log of n. All right, now we just have to think of how many answers per chunk we need to potentially store. And the answer to that is log squared of n. That's how many set bits there are per chunk. Log squared of n. So we end up with this big O, right? This is the maximum number of sparse chunks we could possibly have. This is the number of bits we need to store an answer. And this is how many answers we need to store per chunk. Right, and so this whole thing, right, this 4 in the exponent here is going to cancel with all, well, I should say the 4 is going to become a 1 after we cancel with all of these, which basically multiply out to log cubed of n. So we have log cubed in the numerator, log to the fourth in the denominator. We're going to end up with just log in the denominator. Okay, which is little o of n. I put this check mark up here, this sort of downward arrow, just to emphasize it's a little o. Otherwise, I know it's hard to visually distinguish. Okay? So for the sparse chunks, it's no big deal. It's no problem in terms of the space budget for us to just go ahead and pre-calculate the answers to all possible select queries within those sparse chunks. Okay, and if you think about what's the array, what's the lookup table we're storing here? So there are n over log squared of n, at most n over log squared of n of these. That comes from multiplying these two terms, the maximum number of sparse chunks and then the number of answers per chunk, and then each of them is log n. All right, so so far so good. We've got 2 lookup tables that we've come up with, but they are both little o of n bits, so far so good. Okay, so before we go any farther, let's map out sort of the top of the early parts of the method as we're going to apply it. We now can see the first few things we're going to have to do in order to perform this select query. So far the strategy is we need to figure out which chunk we're in, which is just a matter of dividing. Remember, the input is a rank. We're going to take that rank and divide it by log squared n to figure out which chunk we're in. We need to know, is that chunk sparse, so we can check. Presumably we've got a little table that tells us whether the chunks are sparse or dense. If the chunk is sparse, then we can now simply look up the answer in this green table that we've made. We're going to look up an offset in that sparse offset table. And that's the answer to the query. We'll just return that. But if the chunk is dense, right, if it has fewer than log to the fourth n bits, then to do, right? We don't know how to do this yet. But so far the space is a little low event, so far so good. So let's go back to this overview slide. All right, so we've done part of it now. So we've gone and actually done this case, so check. Now let's go down this other branch where we have to consider the dense chunks. Okay, and in particular we're going to do the next case we're going to handle is the dense chunk sparse subchunk case. Okay, but let's talk first about what is a dense chunk. All right, so we know that the dense chunks are shorter than are the ones that are shorter than log to the fourth n bits. But the next step is we're going to take those dense chunks and we're going to further subdivide each dense chunk into subchunks of square root of log n set bits. Okay, so we're dividing into subchunks where the subchunk size is governed by the number of set bits, and whereas for the chunks that was log squared of n set bits, for these subchunks it's the smaller quantity, square root of log n set bits. Okay, so we're going to divide. Let's say, these are all the chunks here, and we drew our dividing line, and so these are the dense ones, the ones that are shorter than log to the fourth n bits. We're taking those, right, here they are over here. Those are the dense ones. And we are dividing them into subchunks of square root log n set bits, okay? All right, so before we talk about these subchunks and we divide those subchunks into two categories according to whether they're sparse or dense, that's coming. But first we want to just write down what would we need, how much space would we need in order to store the offset at the beginning of each subchunk. Really, it's going to be a relative offset. So now we're dealing with relative offsets. So how many bits do we need to store relative offsets into these subchunks? That's the next question. So here we go. Let's just pretend there's 4 subchunks per dense chunk. And so I've got these 4, each of these are divided into 4, and I've got these 4 relative offsets that I need to store. Okay, now notice that I've shifted from saying that we're storing offsets, like we were saying for the sparse case. Now I'm saying we're storing relative offsets. Well, why do I say that? Well, because now, because we know that we're within a dense chunk, we know that the chunk we're in is no more than log to the fourth n bits, which means we can now bring back that same trick that we talked about with respect to Jacobson's rank, where we said that we can store, with Jacobson's rank, we said we could store a relative rank with log n bits, big O of log n bits. Similarly here, now that we know that we're within a dense chunk, we know that we can store a relative offset, relative with respect to the beginning of the chunk, in log n bits. So I've switched to saying relative offset, and we'll use that fact in a moment. Okay, now at most, how many subchunks are there in the overall bit vector? Well, it's plausible that every chunk is dense, right? If the overall bit vector has many set bits, the majority, if almost all the bits are set, then almost all the chunks are dense. Let's say that all the chunks are dense, in which case we have the maximum number of subchunks, which is going to be, and if we say that the number of set bits might be approaching n, it's got to be n over square root log n. All right, so we were going to say that we have at most n over square root log n subchunks. And as we were just saying, the containing chunk, every subchunk is in a dense chunk, and we know something about how large the dense chunk is. We know that it's less than log to the fourth of n bits. So that means, again, we can use the usual trick. We did something just like this with Jacobson's rank. Okay, so how many bits do we need to store a relative offset? Well, we only need to describe offsets within a dense chunk, right? So that's going to take log of log to the fourth of n bits. But remember, when we have the log applied to an inner log, and that inner log has a constant exponent, that exponent comes down, becomes a multiplicative constant, and then is sort of swallowed up or ignored by the big O. So we can just write this as big O of log n. Okay, bits. So since we're within a dense chunk, which has less than log to the fourth of n total bits, we can store a relative offset relative to the beginning of the chunk and use big O of log n bits. So overall now, let's combine these. All right, we have the n over square root log n, right? That's the number of the maximum, the worst case number of subchunks, the maximum possible number of subchunks. And then the number of bits we need to store per subchunk to get the relative offset to the subchunk is log. So we have big O of n times log n over square root log n, which is little o of n. Bits. So overall, we're good. We're safe to store not only, as we did before, the offsets up to each chunk, but also the relative offsets up to each subchunk for the dense chunks. Okay, all right. So far, so good. Let's actually, so as to keep ourselves anchored, let's go back to the outline of the method again. Right, we already discussed finding out what chunk we're in, which is just dividing by log squared of n, dividing the input rank by log squared of n. We already know what to do in the case of a sparse chunk. Now we know at least a little bit of what we want to do for the dense chunks. So first of all, we have to look up the offset of the chunk. And we already talked way at the beginning about how we would store chunk offsets. Then we want to find out what subchunk we're in. And then we can look up the subchunk's relative offset. All right? So if we wanted to give an answer to the question, it would be this plus this, but we're not done. It's also now, we're within the subchunk somewhere, so we have to deal with what we have to deal with the relative offset into the subchunk to exactly the one bit that we're trying to select. Okay, so now we need to look within subchunks. Okay, and this is what causes us to do our final split between sparse and dense, right? Sparse subchunks and dense subchunks we'll have to handle a different way. Okay? So the new dividing line between sparse and dense is going to be that subchunks that have at least 1/2 log n bits are the ones that we're going to call sparse. All right? And it's perhaps not surprising that it's going to be that log n is involved, because after all, the number of set bits in each subchunk is square root log n. And like we like to say, the dividing line between sparse and dense is generally whether more or less than square root of the number of bits are set. Now there's this 1/2, but that perhaps also shouldn't surprise you, because you might remember that in Jacobson's rank, for the dense case, right, it was valuable to have this 1/2 log n, because we ended up plopping it into the exponent. We said 2 to the 1/2 log n is special because you end up with square root of n, right? So you end up with something that's sublinear in n. Okay? All right, so which are the sparse subchunks? They're the ones that have at least 1/2 log n bits. And for those, we're simply going to store the relative offset for every set bit in the subchunk, right? Just as we stored the offsets for all the set bits and the sparse chunks, we're going to store the relative offsets for all the sparse subchunks. So how much space is that going to be? Let's go through this usual exercise of doing the big O and multiplying a bunch of stuff together. Okay, so what's the maximum possible number of sparse subchunks? Well, they all have at least 1/2 log n bits, so that's going to be n over 1/2 log n. Okay, how many bits do we need to store one of these answers? Well, because it's a relative offset, we know that it's log log n. We just discussed that in the previous slide. And then how many set bits are there per chunk? Square root log n. Oop. Okay. There we go. So what does this end up being? We need to convince ourselves that this is little o of n at the end of the day. So let's keep trying to simplify this. Let's gather everything up on top. N square root log n, log log n, all that on top, over log n. I lost the 1/2 since it's a multiplicative constant. Just got rid of it. Okay, maybe we can simplify this a little bit more by dividing top and bottom by square root log n. Okay, that's going to give us n log log n in the numerator, square root log n in the denominator, which is little o of n. Bits. That tells us it is okay to simply store the answers, the relative offsets with respect to the sparse subchunks. Okay. Great. All right. So yet another lookup table. This lookup table is going to give us the relative offset within each sparse subchunk of any possible bit you might be asking about. Which takes care now of all the parts on the diagram you see here. There's only one, so check. There's only one left. We need to handle this case, the dense chunk and the dense subchunk. The dense subchunk of the dense chunk. Right, so let's handle this one. This is, just like with Jacobson's rank, this is where we're just going to make an enormous lookup table, basically for all possible dense subchunks and for all possible queries, all possible bits that we could be asking about. We're just going to write down the answer, right? All possible, which means that the answer, when it comes down to a dense subchunk, is going to be a lookup. Okay, so subchunks that consist of fewer than 1/2 log n bits are dense. For these, we're going to pre-calculate the answers for all such chunks, just like we did with rank, right? So how many possible dense bit vectors are there? Okay, well, 2 to the number of bits, to the maximum number of bits. So that's 2 to the 1/2 log n, right? Which is where, looking ahead, this 1/2 is going to help us out here, all right? So that's the possible bit vectors, okay? Now, how many different queries are possible, right? We're trying to do a select for one of the set bits within this dense subchunk. And there are exactly square root log n set bits in that dense subchunk. So the number of possible answers we have to store is square root log n. All right, those are all the possible 1 bits, possible set bits. Okay? And then for each of them, we have to store a relative offset, which is log log n bits. Okay, so what do we have in terms of a big O? We have to multiply these things together. First thing we have to remember is that when we have 2 to the 1/2 log n, all right, we can think of that as 2 to the log n to the 1/2, right? 2 to the log n is n. So we have n to the 1/2, which is square root of n. So the possible bit vectors is going to come down as a square root of n factor. All right, now we've got this square root of log n, so I'm just going to extend this and put log n in here underneath the same square root. All right, and then we've got times log log n. bits. And that's little o of n. So that makes this part of the process, it just turns it into a lookup. We have a table with all possible combinations of bit vectors, one set bits, and answers to the query, where an answer is a relative offset into the subchunk. So this gives us our final lookup table. We now have all the lookup tables we need, and the overall flow of what we want to do looks like this. You've seen this before. Okay, so the very first thing we're going to do is figure out what chunk we should be looking in. So we take the input rank divided by log squared of n. That tells us which chunk. If the chunk is sparse, then we can simply look up the answer, because for the sparse chunks it was possible for us to store answers to all possible select queries without exceeding our little o of n budget. If, however, the chunk is dense, then we need to look up that chunk's offset. Right? We're in a dense chunk. We now need the chunk offset, because that's going to be something we need to add to all of the relative offsets that we are going to find later. So we've looked up the chunk's offset. Now we need to determine what subchunk we're in by taking our sort of relative rank within that subchunk and dividing by square root log n. Okay? Now for that subchunk, we can look up its relative offset, because we stored all those. And now we have the remaining problem is we need to find out our relative offset with respect to the subchunk. Two cases. One case is that the subchunk is sparse. In that case, we can look up the answer, because we can simply store answers to all possible subchunk relative offset queries. Other case is that the subchunk is dense. In this case, it's also just a lookup, except in this case, the lookup table is all possible dense subchunks, and all possible queries are stored. All right, so that's our approach. And this approach relies on these 5 data structures. But the other thing to notice is that there's no loops here, right? There's nothing that's being done repeatedly. And each of these steps is going to be a constant time operation. It's either a lookup, or it's a division, or it's something else that you can easily imagine is going to be done in a constant number of machine instructions. Here are all those data structures. I just wanted to show them all on one slide. These are the 5 lookup tables we made. The sparse chunk offsets, the offsets for all the set bits within each of the sparse chunks, right? The dense subchunk relative offsets, and then for the sparse and dense versions of those subchunks, we have the lookup table that has answers just for the set bits, and then we have the big lookup table that has answers for all possible dense subchunks and all possible queries. Okay, so with that we have what we wanted. We have a algorithm and set of index data structures here, so that if we put them together, we can answer select queries in constant time because there's no loops here, there's just a constant number of steps we have to go through, and each of them is constant time. It's little o of n because each of these 5 data structures are little o of n bits. And therefore, we can fill in the select row of this table that we discussed last time, right? Jacobson's rank lets us say that this is possible, constant time, little o of n space. Clark's select lets us say that this is possible, constant time, little o of n space. Access was already trivially constant time and trivially requiring n bits, because we're simply storing the bit vector. And so this is actually the dream, right? When we were talking through those sort of halfway solutions where we would store, for example, the answers to all the select queries, and then we would do binary search to answer rank queries and things like this, we ended up not being able to achieve bounds like this. So the ability to do constant time and little o of n space for rank and for select is now a crucial toolbox. We need to expand the toolbox so that we can go beyond just bit vectors. But it's a crucial toolbox that everything else is going to build on top of.